Okay, good evening everybody. I hope everyone's having a wonderful day. So before I get started, I just wanted to make sure to remind you, remember the first assignment is, its due date is coming up very, very soon. Other than that, one thing I also want to bring up is that assignment 2, it'll be out sometime later on, I guess tomorrow. It'll be out a little bit later on tomorrow, okay? So just as a reminder, the second assignment is a programming assignment. So if you're like, man, I want to do some coding, yeah, you'll get some opportunity next time. It should be, I'm hoping you'll find the problem pretty interesting. So that being said, I want to talk about recursion today. So let's talk about recursion. So I know before this class, I wanted to sort of get a feel for where everybody is on the subject of recursion. So I'm just going to really kind of give us a kind of a general overview, and we'll talk about some examples of recursion too. So you're going to find this topic both very helpful for thinking about ways of solving problems, but also as a tool for programming. So it's double-edged like that, with its own pros and cons. So you might ask, what is recursion? So recursion is a way of defining, man, am I looking at this marker, man? I might need to change it. Recursion is a way of defining a function in terms of its own definition. So at first you might say, Dan, that seems really self-referential. Like it seems like a very interesting idea. You may or may not be familiar with the idea of recursion. So I'm going to be trying to show you some examples of this today. So let me just switch to a different marker. Hope that this one's a little bit better. I don't want to have to start launching markers. So the big thing I really want you to really take from this topic, there's kind of a couple of things. So it gives sometimes. Okay, this marker isn't it's probably no different. Did somebody like jib my markers while we're doing this? Anyways, it gives sometimes a natural way to describe algorithms. Yeah, I'm definitely switching to a different marker. Okay, this one's not very fun. Let's switch the marker. I think this one's not very good. It's gone. It's gone. So let's get a different marker. It was. The turtle friend, by the way, decided to take a little nap over there. So if anybody wants to say hi to our little turtle friend, our turtle friend's just down over there taking a nap. Yeah, banished to the Shadow Realm. Yes. It was time to duel. Yes. So let's see here. Let's see. Where was I? I was talking about recursion. And keep in mind that these kind of algorithms that use recursion, we would describe these as recursive algorithms. So if somebody asks you, can you give me a recursive algorithm? It's an algorithm that uses recursion. So we refer to these as a recursive algorithm. And again, another funny marker. So let's switch to a different marker. I got like 7, so I'm hoping I'll get a good one. And I must stress that sometimes it gives a very natural way that's also very elegant and simple. I'm going to hopefully give you some examples of this today. But also you can think of this also as a way in programming to solve problems. So you can use recursion. It's not just some abstract concept. It's very real. In fact, recursion is sometimes even how some programming language actually, they define what functions are. Sometimes they define them in that way. So there's often a recursive algorithm. So recursive algorithms have two parts typically. So recursive algorithms are composed of two parts. So very often when you design a recursive algorithm, you're going to try to identify these two parts. So the first one that I'll point out is the recursive case. So the recursive case, this is just where you specify a solution. A solution is expressed in terms of solving. I have the worst luck with markers today. In terms of solving a smaller version of the problem. So you might ask, what does that even mean? Like, what does it mean to have a smaller version of the problem instance? So what's going to happen is I'm going to describe a function, and the way I'm going to solve it when it's rather big, I'm going to try to describe a way to solve the problem, but in terms of using the exact same function again on a smaller size of the input. Whether it be a range of the input, whether it be that I just make the input smaller. The point here is, as I said up here, it's going to be defined in terms of itself. However, you might naturally say to yourself, well, like it truly can't be defined entirely in terms of itself. There's got to be some way I eventually get down to solving an actual problem, right? Because all this is saying is that the solution's expressed in terms of smaller version, right? So how do I solve the smaller version? So this is where your base case comes along. So this is the other part. So this is the base case. So this base case, so it's simply a way to solve the problem as presented, or either way, I give you some solution, so some way you can get the answer. And usually it's that it's sufficiently small, meaning it's usually going to be a very small constant number. So it's sufficiently small. So it's going to be sufficiently small without reference to itself. Without reference to itself. So to be very clear, in this case, what will happen is I'm going to end up calling I'll call at least one function in this case, and that will be what we're going to refer to as a recursive call. So if ever I try to solve one of these smaller versions, I'm going to call a function recursively. So this is what I'm going to refer to as a recursive call. The base case is not a recursive call. It's actually going to directly solve a problem, but it's going to be usually a much smaller version of the problem. So that the idea is that if I could tell you how you could solve the problem in a smaller way, I could eventually break the problem down into a smaller and smaller and smaller pieces, so that when I get to the base case, which tells me exactly how to solve it when it's small enough, I know some way of answering the whole question. You're going to see what I mean in a moment, because at first it sounds a little bit strange. So I must stress that you may start, for example, at the base case and then work your way up using the recursive case to build up larger and larger instances that you're going to solve. Or you usually may start with the recursive case and work your way down to get down to the base case when your problem is small enough to play around with directly. So it can go either way. It goes both ways when it comes to dealing with the recursive case or the base case. So does everybody have a general idea? So just remember, keep in mind, look out for a recursive case and base case when I start talking about some of these examples. I'm going to first start off with something that's a little bit more basic. I want to encourage you to think more like something that is recursive. So I'm going to do a couple of quick examples. Actually, let me do one first, just to kind of give us a flavor for what I mean by recursive. So I have some lovely friends here. This is my gang, by the way. Shrek is my homeboy, but I'm not supposed to say his name. But anyways, the point here is, suppose I have my friends here. And I want to know how many of my friends I have here. Now you can clearly see there's 4 friends I have. I only have 4 friends, that's it. So they're pretty epic friends, but most certainly I have 4 here. Now, can somebody tell me a way I could count my 4 friends out? So suppose I have like a clipboard in front of me. What can I do with my clipboard to count my friends? Like, how do I find out that I have 4 friends? Imagine if I had more than 4 friends. Say I had n friends. Any ideas? Just think of the first thing that you might try to do with a computer program. Yes, so think of it in terms of a for loop. So yeah, so you could, imagine if you had your friends like an array, for example, you can go through and check if you have a friend in there or not, right? You can count them, but naturally the first thing you're thinking of trying to do is I come over here, I'm going to do something kind of meta, I'm going to walk over here, and say I have my clipboard over here. I don't know, I'm going to start off with a count of, I have 0 friends right now that I've counted. And suppose I start here, I have this lovely, lovely dog here. I could say, okay, I'm going to make a record for myself that I've seen 1 friend so far. And look, here's the next one. I have 2 friends here. So now I have 2 friends. Then I'm moving to the right here. Oh, I see I have a lovely cowboy friend. I have 3 friends. And lastly, I have this lovely large friend I have 4 friends. Right? So I can go scan from left to right and I can count them, right? So that's a very natural way of thinking about how you might count all your friends. Now, so does everybody understand that that's one way I could count my friends, right? Is you could think of it, and this is the way I would like to encourage you to view this, is that that's a very iterative way of solving this problem, right? I go through for each of my friends, I see if I have a friend there. If I have a friend, I include it in my tally until I've gone through everybody. So this is what we will refer to as an iterative solution for counting my friends. So just to be clear, when I mean iterative, I mean this. Iterative. So this is talking about things like for and while loops. So here's another way I could count my friends. So suppose I feel really lazy. Say I didn't want to get my clipboard out and I wanted to go count all my friends. Okay, I could start right here at this friend. And I know I have 1 friend right here, right? So each one of my friends, they are 1 person, right? So what I could do is I could say, for example, ask my friend here, I could say, hey, look, can you tell me how many friends are to your right? And sure enough, I know I have 1 friend here, but this friend asked this friend. And this friend says, hey, look, I'm a friend, right? So, but so maybe I need to find out how many friends I have. Well, I haven't yet figured out how many friends there are in total yet. So I'm going to ask my friend to the right to tell me how many friends there are right now. So I get to my friend over here, my lovely cowboy friend. I now have the question here. Well, this is obviously a friend. At least I hope. Hopefully I'm not that lonely. So I have my lovely friend here. Well, my friend here can ask the friend to the right, hey, are there any more friends? And I get right here, I can ask the exact same question, right? Hey, look, do I have any friends to my right? The answer in this case, no, I have no more friends to my right, but I'm a friend, right? So I know that I have one friend so far, right? So what this friend can do is pass along that message over to this friend and say, hey, look, there's one friend to your right, but hey, look, I'm a friend, right? So that means there's so far as 2 friends that I know about, right? So far I have 2 friends. Likewise, I can pass along that message to my lion friend here. And I could say, hey, look, there are 2 friends. How many friends are there? Well, there's me and those 2 other friends. So I better pass along to my lovely chef dog friend over here. So now I so far have passed along that I have 3 friends. And hey, look, remember, I'm a friend, right? So it means that I have 3 friends plus myself. So that means I have 4 friends in total. And hey, look, this is the first person I asked, right? So my friend here passes along and tells me, hey, look, you have 4 friends. Deal with it. So at the end of the day, I can find out how many friends there are without having me walk around and go tally them myself. I can give them a recursive procedure for doing this. So every time, there's kind of 2 things to this, right? So in the recursive case, does anybody have any ideas of what actually, before we get to the recursive case, let's think about the base case. So what would the base case look like? Does anybody have any ideas? So think of like the smallest problem of what I'm doing here. So think of the smallest problem that you can have. So how many friends would I be trying to count there? Yeah, it's when I have 1 friend, right? Now keep in mind, you can also make it so that you can ask nobody and see if nobody has any friends. That you can do, but I want to keep it very simple. So notice that when I get to my lovely friend from the swamp, when I get to this friend, notice that there's no friends to my right, there's only me. So what I pass along, I just pass along 1, right? So this would be a lovely base case, is when I have no friends to my right. However, when I have a friend to my right, what did I do? I get the count of how many friends are to my right, and then I add 1, and that's what I pass along, that's what I return. So in that case, that's what the recursive case is. Does everybody sort of see the idea here? Is that instead of me having to say, oh, look, I don't have to solve this entire problem at once. I can just break it down in terms of itself. In this case, I can simply ask, hey, do I have a friend to my right? If I have a friend to my right, okay, find out how many friends I have count up how many friends I have, and then add 1 to it. If I have no friends to my right, I could just simply say there's just me. So this is one example of recursive thinking as opposed to iterative problem solving. So instead of thinking about it like I go through like a loop, you could think of this now as I have a process where I can think of it like I can do something that makes the problem a little smaller, or I extend the problem. So there's 2 ways you can think about it, just like I said before. I could even view this in a different direction. I could start off with 1 friend, and I could give you a process for counting as many friends as you like using the exact same process, right? I can start off with 1 friend, and I can ask if there's any friend to my right. And then I get to say, hey, look, now I have 2 friends. Do I have a friend to my right? Okay, then I'm going to reapply this process again, and I could actually count them this way as well. But you might look at this and say, Dan, well, that just sounds like you're doing something like a for loop or a while loop, right? there's actually a very interesting connection between linear structures or linear processes like this and loops. Oh no, I lost my lovely friend. This is why they don't want to hang out with me. But that's just an example demonstration, just to give you the idea that you can talk about how to solve a problem in terms of itself by making the problem a little smaller every single time. And then eventually we get it down to a small enough size that we can solve it directly. Or you could take the very small problem and you can always extend it by one. Yeah, I only have 3 friends now. Oops. So anyways, so just when we do these examples, keep in mind the idea here. You want to try to identify these 2 places. Yeah, no. My lovely friend from the swamp went to go hang out with the turtle. That's the way I'm going to put, that's the story I'm going with. Nobody tell anybody else, okay? So anyways, let's start talking about some examples here. Because at first this might be like, okay, this seems rather like, sure, you described that, but what does that actually look like as actual code? So let's talk about that. So let's talk about some examples. Oh, let me enable the transcription. There we go. There we go. My apologies. So you may have actually seen some examples of recursion before. If not, these might be things you can think about. So here's a first example. So let's talk about summing. Let's talk about, say, for example, if I was trying to compute a sum. So consider if I wanted to add 1 plus 2 plus 3 plus 4 plus all the way up to n. Now, you may know several different ways to do this and compute that sum. In fact, we have a formula for this, right? There's several different ways you know how to compute this. If you were to write up a computer program, you could think of a couple different ways to do this, right? So for example, just as an example, you could do this with a for loop, right? So here's just some code here, just to give you an idea. So if I have, say for example, I want to return the sum, I can have int. I'm going to call the function iterative sum. So I must stress that this is actual C++ code. And it will be in the notes too, if you find yourself wanting to just like plop this into a code editor, okay? I just want to make sure you see a little bit of code when we're doing this, so you get the general idea. So I'm going to make a variable that counts a sum. So I'm going to start it off at 0. And what would I do to count up these numbers? I know that you know how to do this. I'm like Santa Claus. I figure these things out. So does anybody have any ideas of how I can compute this sum using an iterative approach? So think of this problem iteratively. So if I use a for loop, what might that look like? Yeah, exactly. You're going to have a for loop that goes like this. You're going to have for int I is assigned to be 1. I is less than or equal to n. And then I could go I plus plus. And then I could just simply update my sum by assigning it to be sum plus I. And then I could just return the sum when I'm done this, right? So this is just a nice simple example of using a for loop. Wonderful. So notice that this is just a nice iterative way of computing this sum, right? Now, I want you to think about this in a different way. So look at that sum I have up there. So imagine I start instead at n. So imagine I start at n right here. This is just some side thoughts for us. So just some side thoughts for us before we get to the recursive algorithm. Well, our recursive function here. So So if I wanted sum from 1 up to n like this, here's another way you could think about it. Well, I could start at n, and then I could sum, say, n minus 1 plus n minus 2 all the way down to 1, right? This should equal the same sum, right? That will give you the same result, right? Now, think of it like this now. So notice I have like 2 pieces here. Now, this right here looks like a very similar problem to what I had originally, right? Except now, n is n minus 1, right? So now what I could do is something quite similar. So if I have this, I can have n minus 1 plus everything else. So n plus 2 all the way down to 1. And I could keep doing this process. Notice I have 2 parts here. I have whatever I'm currently wanting to add, and then I have whatever's left. So I must stress that we're not necessarily looking for the fastest way to do this. We're just trying to see if we can understand this through a different way of viewing the problem. So that's what I'm trying to encourage you to do here. So when I think about this instead recursively, now keep in mind the fact I started at n doesn't matter. I could have made this 1 plus 2 and so on and counted from the bottom up. It doesn't matter. But I'm going to choose this approach, and I can think about this actually recursively, just like my example with my friends. It's actually very much the same idea. Does everybody see that? There's actually something very subtle I'm doing here, is that I have myself, and then I have everything else I want to get done, just like when I had my friends to the right. Does everybody see that? Isn't that kind of neat? So just like I have myself, and here's all the rest of the stuff I could pass along to my friends to the right. Notice it's the same idea again. It's just I cloaked it in a different problem. Is that kind of neat? So let me describe how we could write this in C++, how we could write a recursive function like this, that does this. So let's head over here. And I'll try to help identify the recursive part in the base, the recursive case in the base case with you. So once you see that idea, it really, you have to think about it in terms of, I have a problem. Is there some way I could define the problem again in terms of itself, while I still try to advance myself towards the final result? Because you have to be careful, as I'm going to show you an example of where this could go very badly. Very badly. So here's how I could write a recursive function that does the same, well, produces the same sum. So I'm going to call it recsum. It's going to return an integer. And I must stress that I'm not going to worry so much about how we're passing parameters or anything like that, just because for our purposes, it's really about understanding the ideas here, okay? So if you're asking, like, why didn't you put const or something like that? Don't worry, I'm not focusing so much on that right now. I just want to make sure we understand the idea. So similar to my example that I had over there in my friend example, notice that I eventually have to stop this process of adding. This is going to happen when n is equal to 1. So I'm just going to, by the way, I'm just going to assume that n is a positive integer just to keep this simple for us. So it's going to start at 1 or go higher. So in this case, what should I return if n is equal to 1? What should I return? So what is the sum where it's just 1? Well, so n is equal to 1, so it's just 1 with nothing else, right? So I'm just going to return 1. And otherwise, this is the case where we have everything else. Now, let's think about what we did before. Think about our lovely lost friend that went on to go have a nap with the turtles. So think about it now. So I would like to return something here. So I'm going to return myself, which that's myself, right? Plus, now I have to write something right here. Now you might ask, Dan, what are you going to write right there? That's got to be really weird. Like it's going to be something. I assure you, it's actually very typical, but it's going to be at first a little weird if you've never seen this before. Yes, exactly. The chat's got this. It's going to be rec sum, where remember, the largest term of the sum that I had over there was the number -1. So now notice that I have two cases here. Can somebody tell me what's the base case, what's the recursive case? So which one is the base case, which one's the recursive case? Yes? Oh, very good. Yeah, so when you're doing these recursive algorithms or you find yourself using recursion, try your best to identify these two cases. Once you do that, it makes your life so much easier. So remember, if you go back to my picture I had over there, remember, if I give you n, now remember, you got to think about it in terms of itself, which is kind of weird at first if you've never seen this idea before. So just like when I went back to my picture over there, so remember I had like n plus n minus 1 plus all the way down to 1. Remember, this was myself, but remember, when I call this function, what's going to happen is n is now going to be this. An easy way I like to remember this is I think about it in terms of some inanimate object or just some fun object. So if you find yourself having a hard time kind of understanding this idea, instead of thinking of n, think of it as a banana. Here's a very horribly drawn banana. So if n's a banana, this is going to be simply a banana less 1. So just like over here, I have a banana here. But now notice that all of this is what I'm applying this is just simply the number of bananas less 1. So the size of the problem went down by 1. So notice that the way we think about this is first, there's two things I want to point out. Remember the base case, recursive case, and notice how the recursive case calls upon the function itself, but it does it with a smaller instance of the problem. That's very important. So just as a question for you, does anybody have any speculations of what would happen if I got rid of that -1? Any speculations whatsoever? Give me your best shot. Yeah. Yes. So notice if you think about this just like you do when you think of calling a function. Yeah, I see the chat's got this. It's just like, so notice that when I recall, say if I call this, say for example, say if I were to call rec sum with 4, for example. Okay, so it's not going to execute this. Instead it goes here and says, okay, return 4 plus rec sum 4. Okay, so how do I compute this? Okay, I call rec sum 4, so rec sum 4 comes down here. It evaluates n plus this, but that's rec sum 4 again. And I noticed it will never stop doing this. In fact, in practice, when you run into this situation, you're going to run into something. You may have heard of this phrase before, and I will justify what exactly and where this phrase comes from. You'll run into something called a stack overflow whenever this occurs. So I'll explain what I mean by a stack overflow a little bit later on. But yes, if you think about it, if I had as much memory as I want, this thing could go on forever. But because our computers are finite in their memory, we're going to run into these weirder practical situations where we're going to run out of memory. And one situation where this happens is the so-called Stack Overflow. So I'll talk more about that in a little bit. But very good, everybody. So I'm going to put that -1 back in. See, nobody's seen it. So question, why will we return 1 though? Okay, remember, so just as a reminder, and I'm going to walk through this process of how this works in a little bit. I just want to give you a couple more examples. So when I call, say, recsum4, what does recsum4 depend upon to execute? Well, if it's 4, then most certainly you're not going to execute this if statement, right? Instead, you're going to go right here, and you're going to try to check if n, so you're going to compute n plus recsum3, right? So you're going to rely, so to compute this, I need to know the result of recsum3, right? Well, what happens here? Okay, well, it's not 1, so it's going to want to know the result of recsum2, right? Because I can't compute this sum until this result is computed, right? So remember, it's just returning an integer, but how can I return this until I've evaluated this function's result yet, right? Because there's no way I could know the result of this until this function returns back me an integer, right? So, of course, recsum3 will then call recursively recsum2, and when I go down to 2, it's going to come back here again. I'll explain in a moment how all these variables play around with each other in a little bit here. But once I call recsum2, it goes down to recsum1. Now here's the neat part. When I'm in recsum1, that's when n is 1, right? So in this case, you know the answer is going to be 1 here. So you know, okay, so I return 1 back to this function call, which it's relying on you to get that 1 back, and at that time it's 2. So 2 plus 1 is 3. So it returns that, and now I can finish off recsum3. Well, 3 plus 3 is 6, right? And now recsum4 is waiting for recsum3 to finish, right? This is really weird at first to think about, because it's a function that calls itself. But the spoiler is that all of these are still function calls. So they follow the exact same rules you're familiar with functions. So just as an example, every time you make a recursive call, when you call one of these functions, any local variables that are sitting in here, they're all tethered to the scope of that function call. So if you have a variable inside of here, like say if you had a variable that's like some counter or something, every single time you make another function call, it will have its own variable that's a counter variable for each function call. They are not the same exact function, the same variable. Each one will have potentially their own value you can manipulate within their own function call, just like any other function call. There's nothing magic that's going to go on that's different here. So when I get over here, when I compute this out, that's why you'll notice that every time I have a different n with each one of my function calls, because I get those from the input. So when I try to compute the recsum4, okay, well, I know the answer to recsum3, so now I have 4 plus 6, and then my recsum4 will return 10 back to the program, and the program can continue executing. So it's a little bit weird at first. I know that's a lot to kind of digest, so I'm hoping that we could do some examples just to kind of motivate and understand just how recursion works a little bit. So far, are we doing okay, everybody? So did this recsum idea make sense for everybody? Just I want to ask because it's important that you see that there's a couple different ways you could think of the same problem. Just one of them is actually being defined in terms of solving the problem with itself. It's just that we try to make use of that fact when we solve the problem. So sometimes it's useful to think of procedures in this kind of way because sometimes it leads you to a much simpler way of describing the algorithms. So like I said, like look at this algorithm. It's actually really simple, right? Notice there's nothing really complicated about what you see here. So what would be the worst case here? Now, I'm not going to focus so much on the worst case analysis here quite yet, but I will tell you up front that if you wanted to analyze the running time of this algorithm, the tip I will give you is that you can first ignore the recursive calls, analyze it just like you did before. So do you know how we count and group the operations? You could do that same exact thing here. You first ignore the recursive call, just treat it like it's some constant operation. And then after that, count up, figure out how many recursive calls can happen at most. Then you just multiply out those results. So take how many operations are going to happen for one of these calls over how many multiply by how many there are. So in this case, notice that if you look at my recursive calls, I just stepped on our lovely friend. So if I do 4, notice I go 4, 3, 2, 1. I have to compute all of these, but how many of these are there then? How many of those are there if I think of n as 4? It's n, right? So if you wanted to know the big O, for example, here, it would be big O of n. So to answer your question, it would be big O of n, which nicely matches up with what I gave over there, right? Except it's a loop. I'll talk about like kind of the trade-off between, let me get my lovely friend. So I'll talk a little bit about the differences between doing those two things. They're not necessarily the same thing. They do things a little bit differently, at least on the computer. But yeah, so a question, the question about how it went all the way back up. Because remember, when I compute this recursive case, what does it do? It's a sum. It has n. I have n, but I don't have this yet. So how do I know how to compute this? Well, I have to compute rec sub n minus 1, right? But this this return statement cannot finish until I've determined what rec sub n minus 1 is. So when you do this, notice that every single one of my recursive calls in the recursive case, every single one of those relies on me computing rec sum for a value that's 1 less than it. So to get the actual answer for rec sub 4, it relies on rec sum 3, that relies on rec sum 2, and then when I get to rec sum 1, well, that's our base case. So you'll notice that once I have this information, I could get this information, this information, this information, and so on. I'm going to show you the direct mechanism your computer uses to make this happen. So at first, this looks a little bit interesting, but I must stress, there's nothing special about these. These are just function calls. They're just of the same function. So just make sure you just keep that in mind. So just don't think of this like it's like a very different mechanism I'm using. It's actually using the exact same mechanisms all your other function calls use. It's just that the functions aren't the same ones. They're calling on the same named function with the same signatures. Okay, so that's one example. Let's talk about another example. So let's go over here. So another example I could think of, I know that you'll see this example in the lab, but maybe in a little while, so I want to show you a little ahead of time. So here's another example. So let's talk about factorial. Now you may have heard of factorial before. You may have seen it in the mayonnaise class. So that's the place where you make really epic sandwiches. Factorial. Sorry, that looked like it melted. Almost like it was made out of a mayonnaise sandwich or something. Factorial. So if you've never heard of factorial, let me define factorial for you. So I'm just going to define it in a simpler way for us. There are some more general ways to define factorial, but I'm going to keep it simple here. For any positive integer n, define n factorial. The factorial is given and written as an exclamation mark. And that's set as n factorial, where n factorial is going to be equal to n times n minus 1 factorial if n is greater than 1. And it's going to be, and 1 factorial is going to be equal to 1 if n is going to be equal to 1. So I've deliberately written out factorial this way. You may have seen factorial defined like this. You may not have. For example, there's other conventions such as 0 factorial equals 1, but I'm not going to talk about that so much here. Now I have a question for you. Is this definition recursive? Yes, exactly. So this is what I really want you to start picking up on, is if you see something that looks like the same problem, but it's defined in terms of something that's a little smaller. So notice, try to look for these kind of patterns. So notice that I have n factorial. N factorial is defined in terms of itself, the n times n minus 1 factorial. It's just like my banana with a 1 less banana, right? So you might look at this and say, okay, well, this right here, if I were to write out a computer program to compute n factorial, this is going to end up being the definition for my recursive case. This right here is my base case, right? In fact, if you were to talk about this in the M-word sense, the mathematical sense, they usually will use these terms to describe factorial when you talk about it like this. Recursive case, and this is the base case. So it's nothing too much different here. So I just want to help motivate really how you could think about this in terms of recursion. So for example, if I have 4 factorial, just to make sure everybody's clear what this definition is, 4 factorial is going to be equal to, it's 4 times 4 minus 1 minus 4 minus 2, and then that's 4 minus 3. This is when it's equal to 1 in this case. But you'll notice that this is just simply 4 times 3 times 2 times 1. This is equal to 24. So this is how you might think about it if you looked at that and thought about it in terms of iteration, an iterative way of doing this. Can somebody just describe to me in high-level language how I could compute factorial using iteration or an iterative approach? Question. So I'll let you think about that. How do you define the base case 1 factorial? So what I'm saying is when n is equal to 1, it's equal to 1. That's what I'm saying. 1 factorial is equal to 1. So I want you to think about an iterative way you would solve this problem, not a recursive one quite yet. Yeah, so I'm seeing what I would expect. Somebody had suggested using a for loop where you start at n or you could even start at 1, for example, and you can simply multiply just like I did over here. See how I have 4 times 3 times 2 times 1? Notice that you could just simply write a for loop so you keep a variable that stores, say, starting at 1, and then you multiply going up, so you're going like 1, 2, 3, 4, you'll multiply your result by each successive term. And yeah, you could just do it that way with a for loop. So that's one natural way you could think about factorial in an iterative way, right? So if you want to think about it in terms of recursion, though, thinking about it recursively by this definition, well, so notice that you can, so an iterative way of approaching this would be using a for loop. However, if you want to think about this recursively, so here's a recursive way I could look at it, I just use this definition directly. Well, 4 factorial is going to be equal to 4 times 3 factorial, right? So if I want to know the result of 4 factorial, I need to know the result of 3 factorial, right? So to know 4 factorial, I need to know the answer for 3 factorial. Well, what's 3 factorial? 3 factorial, this is 3 factorial is just 3 times 2 factorial, right? So to know the answer to 3 factorial, I need to know the answer to 2 factorial. But notice every single time my problem gets smaller, I'm trying to get to this base case. So I don't want to have it where 4 factorial is equal to 4 times 4 factorial, because that's 1, that's not the definition of factorial, but 2, it's going to be defined entirely in terms of itself. We want it to eventually get to some base case where we actually know how to solve the problem easier. So 2 factorial, just simply 2 times 1 factorial, right? And 1 factorial is equal to 1. So notice that if I'm thinking about this recursively now, if I wanted to do this to determine 4 factorial, okay, 1 factorial is equal to 1. So now I'm just going to replace the answer to 1 factorial as 1. So I have 2 times 1 now, and now I could get the answer for 2 factorial, right? The answer to 2 factorial is 2, right? So I don't need this anymore. So now I can compute 3 factorial, because now I know how to compute 2 factorial. So 3 times 2, that's 6. So now I know how to compute 3 factorial, that's 6. And if I compute this result, I end up with 24, just like I did right here. So does everybody see how you could think about this very much in the exact same way I did in my previous example? So this is one natural way you could see recursion playing out. You could view it in terms of a loop like this, or you could view it very much like I did here, recursively based on its definition. Sometimes there's a benefit for doing this, but you might naturally ask one question. If I have so notice every single time I did this, I asked you, can you do this iteratively? And then I asked you if you could do it recursively. For all the so if you give me something that is recursive, like you give me a recursive way of approaching this, there is a way you could always convert this into one that is iterative and vice versa. So it's not like you don't get one or the other and they're their own things. There's a way you can convert from one to the other. I'm going to hopefully have time to show you the mechanism that makes this work. And believe it or not, the data structure that makes that work is the first one I talked about in this course when I started doing examples, believe it or not. So another example you may think about is here's another example. And it follows the exact same principle as my factorial example. You may have heard of Fibonacci numbers. So Fibonacci numbers, this is a well-known number sequence. So you could define, so I'll define it as fib n. So fib n is going to be defined as fib n minus 2 plus n minus 1 plus fib of n minus 2. So this would be the case. So when I have this case, this definition is when if n is greater than 2, where fib 1, so fib of 1 is going to be equal to 1, and fib of 2 is going to be equal to 1. So question, are there problems where only recursion can be used to find a solution? Now, that is a giant rabbit hole I could go down, but I think at the level we're discussing, if you're dealing with recursive algorithms where you have an actual recursive algorithm and you have there is a way to always translate those types of algorithms into iterative ones. Effectively, what it does is it simulates the recursion using a data structure. And likewise, if I have an iterative approach, I could simulate that using recursion. This approach is usually, actually very often, the approach I described before where okay, I'll mention it in a little bit, okay, everybody? But to answer your question, there is some very abstract things I could talk about involving recursion, but that's going to be way beyond the scope of this course. Like, I mean, even above like a course like 340. But yes, for the purpose we talk about and the way we design our programs, the answer is yes. So there will be ones that always, sorry, to answer your question, every iterative solution has a recursive one and vice versa. You could always go back and forth for at least the types of procedures that we're dealing with here. There's some really out there kind of stuff that's way beyond the kinds of computing that we think of. But that's beyond this course. So I must stress that based on this, you might be able to tell me very quickly, what's the recursive case? What's the base? Well, in fact, we have two base cases. Actually, I already answered the question. So there's the base case. Sorry, that's the recursive case. Then we have two base cases here. Can you see how somebody could write up the recursive algorithm using this information? It might look very similar to the one I did previously, except instead you'll have one if statement for when n is 1 or n is 2, and then you might return 1. And then otherwise, you're going to return fib of n minus 1 plus fib of n minus 2. So you could do the exact same idea with our factorial example. In the notes, I'm going to include pseudocode for both of these examples. So take a look at that. So just take a look at that as I absolutely decimate the lecture area. So I'm going to say C notes for pseudocode, as I'm absolutely decimating the lecture area. I took out our little green friend. I'm going for the whole scene. So before we proceed, are there any questions? So now what I want to do is reveal how recursion actually works. So you get general flavor from the way I formulated these that, oh yeah, when I compute one thing, it depends on usually the smaller bit to be computed, right? There's a very natural way on a computer for how this is done. So let's talk about that. And like I said, it's not going to be anything special. It's just going to follow the same kind of rules that when you call a function on a computer, it will behave the same exact way as what we've been doing with all of our examples. So let's talk about how recursion works. So I'm going to give you an idea of how this goes. So how does recursion work? So that's what we're going to talk about here. So when you have a program and you're going to execute the program, there's a very important aspect of what's allocated to the memory. So for example, in your RAM on the computer. So there's something called a call stack. It's also sometimes called the runtime stack. You may have heard of it before. Oh, I forgot to move the camera. Thank you. I'm talking way over here. That's actually really funny. Let's go back over here. Come on. I'm just hanging out over here with my friends, okay? See, I got the whole crew here. So let's talk about this. So what does recursion rely on a computer? It relies on the call stack. The call stack. And sometimes this is called the runtime stack. Yeah, the whole gang is here. Yes, the whole gang's here. So sometimes this is called the runtime stack, depending on who you talk to. I'll just refer to it as the call stack for simplicity because it involves the calling of functions. So the call stack call stack is used to store data needed for methods or functions. While the program is running. This includes the following. So every time you make a call with a function or method, it's going to include some information that's going to go into this so-called call stack. And remember, this call stack is a part of the active memory on your computer when you're running the program. So you may have talked about this in 115 a little bit when you maybe talked a little bit about data management, when you use like keywords like new or other things like that, where there's something called like heap memory, possibly. It's all the places where you allocate things using the keyword new. And then there's some other parts of the memory that get used, for example, for your code. And yes, and one part of this key part is the so-called call stack. So this is going to be responsible for all these function calls that happen during the execution of your program. So that'll include the main function, the one that starts up your whole thing. So each one of, so what's the data it's going to store with its methods or functions whenever you call them? Well, it's parameters. So I must stress that I'm also referring to the actual value of the parameters when I say this. Local variables, so every time you call a function, this call stack is going to store the local variables that are associated with your function. So every time you make a function call, if you have local variables within that function, it stores its own copies of those local variables. So you notice that when I did my recursive calls, I didn't, like the n within the scope of it always was local to the function call itself. It wasn't a global variable, for example. It's local to the function call. And this is true for any local variables you do designate or declare. So every time you do this, you'll have your own copies of these variables. So sometimes for practical considerations, every time you make function calls, if you make a lot of function calls, you can actually allocate a lot of memory if you make many function calls if each one requires a lot of memory. So sometimes you may even run out of too much, like you may use too much memory in this process. Another thing that gets stored is the return value. So once it's computed, the return value. And the last one, this is more of a technical one that I have to acknowledge, is the memory address. It's the memory address of where to return to continue executing. So to continue executing. So when I have a function, I'm currently executing this function, I need to know some way, like where do I need to go? What address do I need to go to resume back to where I was executing my program previously? That's what I'm referring to here. So when you call a function, you look at your lines of code, for example. When you're actually running this runtime style, you need to know where, like, okay, so if I call a function, I need to know need to put my finger where I need to go back to when I'm done executing my function. So that's what I mean when I refer to this. So just like when you call a function on one line in your main function, you want to know where you come back to in your main function to continue executing the program. This is what I'm referring to. So every time I make a function call, I need to know where I need to come back to, hence is the place where I started. So you might ask what all this data comprises. So we have a name for this. Whenever a function or method call occurs, an activation record. Sorry, my marker is being a little funny. An activation record. Sometimes this is called a call frame or stack frame. An activation record is created. It's created and pushed onto the call stack. So you remember me talking about a push operation, right? You remember I had my stack of bowlish plate looking things? I had my plates and I was stacking them and I talked about a push operation, right? That's the exact push operation I'm talking about from when we talked about at the beginning of the class about a stack. That's the exact operation I'm referring to. So stacks play a very important role in the execution of computer programs, for example. In particular, their memory management. So this is one place where a data structure plays a very key role in the execution of all your computer programs. Isn't that kind of cool? So you might ask, okay, so you talked about pushing things onto the stack. What happens after this? So, like I said, this happens during runtime. Just like you have other things that might be allocated to so-called heap memory. That's the other parts where you dynamically address and you use the keyword new. You have some things that are sitting out in active memory in certain address spaces. But the big thing I want you to note is that whichever function is on top of the stack is actively, sorry about that weird noise, is actively being executed by the computer. Yes, there is a cat lurking around here. Maybe I'll grab her after class and I'll show you. But anyways, the big idea here is you're going to have this call stack. Whenever you call a function, it pushes an activation record onto the stack. So when the program finishes executing, what operation do you think happens with the call stack when that function finishes and ceases? A pop, yeah. Whenever you're done executing a function, a pop operation happens. Exactly. See, you guys all get it. Yeah, so when you do the pop operation, you may release the memory if it's stuff you can get rid of. But I'm not going to get it too much into the details of that. That's more reserved for more of a systems class. There's a lot of under the hood kind of stuff we could talk about here. Like, I mean, way deeper for systems level stuff. So, the big thing I really want to hammer in, recursion is no different than any other function calls you do. There's nothing special about it. Whenever you make function calls, they all use the call stack. All of them. So, that being said, when you use recursion, the order in which you carry out operations may matter. It highly is dependent on the way a stack operates. So whatever is the most active recursive call you made will be ending on top of the stack. And every time you make a recursive call, they keep getting stacked on top of each active process as we do this until we hit the base case. So let me draw you a picture just to see here. So just to be very clear, the call stack is a part of our runtime memory. This is true for any computer program you're going to run. So it doesn't matter if it's recursion, doesn't matter if it's not recursion. My point is recursion's nothing special. The only thing that's special about recursion is that we're calling functions that are given the exact same names and signatures as the ones that we define. So let me draw you a picture just to illustrate this point. So I want to walk us through that example we did earlier on. You know how I drew a picture where I was going through each one of the calls where it said, this depends on that, right? To do the calculation. I want to show you how this actually operates with the call stack so you can actually see this. And I encourage you, if you find yourself just being a little skeptical of this, try on your computer, try to take one of those recursive functions and see if you were to, say, for example, trace through those functions and see if it looks like something like a stack, the order in which they're executed. So just, for example, print off, for example, what the input looks like every single time you call the function recursively. So just as an example, just to illustrate this idea. So if I give you, say, we had recsum, right? So suppose I call recsum with 4. So suppose I call this, say it's called from main. So suppose it's called from the main function. So my call stack, now I'm not going to get too much into the details about the systems level stuff, what's happening around with the main function. The main point is, pun intended, when I call main, it's on the call stack. Any of the local variables you have in your main function, they're all going to be having their own copies inside of here. They're all allocated to in terms of the stack memory, what's in our call stack. So, could go back to the other board for a second? Sure. In fact, I should be able to talk a little bit about this. So remember my picture I had previously. So remember I had it where I did recsum 4, and then recsum 4 depended on recsum 3, right? So whenever I perform these operations, what happens? Well, each one depends on a smaller instance of the problem, right? So let me just pause that. Is this good enough? I just want to make sure. But yeah, no, so I'm just going to kind of walk us through this call stack example. So actually, let me just draw it over here for the purposes of time, because we're starting to run a little low on time. So I have, say, my main function that gets called. That's what I do when I start up the program. There may be some other stuff that I'm not going to refer to. Notice that this is my call stack. When I call main, this is at least what's currently on the top of the stack. So remember, it's like stacking plates. So in here, I have all the local variables that I would have for my main function. If I had parameters, like say, for example, I had some parameters for these would be stored as their actual values in here as well. And it would have, obviously, the return value once it's computed. So when I call recsum 4, so from my main function, I'm going to call recsum 4. So I'm going to call recsum 4. So I call recsum 4. Well, recsum 4 has its parameters, right? Well, n is 4, and we don't have any other local variables, so I'm just going to indicate the return value. So I'm just going to abbreviate that as ret. So to compute recsum 4, remember we talked about this before, it recursively calls recsum 3. So recsum 3 is called as a function. That means it gets pushed onto the stack, meaning that I'm going to cease computing this operation. I'm going to proceed now to deal with recsum 3. And recsum 3, well, when I create this activation record, its input parameter was 3, and I haven't really determined the return value quite yet. I don't know that yet. Well, since n is 3, I don't do the base case yet, so it means I'm going to require computing recsum 2. So I'm going to create a new activation record when I call that function. which that will be for rec sum 2. Its input is 2. I haven't determined what the return value is quite yet. But notice that I'm not popping anything yet. Notice that if I had several recursive calls that could happen, keep in mind that whatever lands on top of the stack is whatever's going to get executed first. So sometimes the order in which you put recursive calls can really matter. So just keep that in mind. So when I call rec sum 2, well, it calls rec sum 1, right? N is 1 here. However, if you look at the rec sum procedure we had, well, what happens? So I'm just going to finish this up, and I'm just going to make a couple of quick remarks, and then we'll wrap things up here. I apologize. I know I want to give you back your time here, but we're kind of in the middle of this example. I want to apologize. This is a really important example. So just keep an eye. If you have to go somewhere, please just check out the lecture video. Just check out that last, like, say, 3 minutes. I do apologize. So this is mostly because we needed a little bit more time. So let's see here. So in this case, it's going to return 1. So what happens? Well, I'm done computing rec sum 1. So it's going to pop. So I'm going to pop off rec sum 1 because I'm done computing that. But now I have the information for computing rec sum 2, right? I got back 1, so I take 1 plus 2. I get 3. And now I'm done computing that operation. I'm done computing rec sum 2, so I'm going to pop the stack. And in this case, I return back 3. Okay, so now I had 3 plus 3 is 6. It returns 6. I pop the stack. I pop the stack. So I had 6. And you get the idea, right? So when we get down to here, we're going to have it where we have, let's see, we had 3 plus 6. But yeah, you get the general gist of this idea, right? Sorry, I'm just wanting to make sure we wrap things up here. I do have a full explanation of this example in the notes, but the idea is now I have what the value I need here is. So you get the return value, you finish computing rec sum 4, it pops the stack, and then now you know where you're going from there, right? Now you're at the main function. So this is actually the mechanism for which all functions, when you call them, operate. And the main reason why I must stress that when I did these return values, every single one of them, when I pop the stack, the return value doesn't necessarily have to go to the one that's immediately below it. I must stress that. Yes. So when you get back to main, when you return, so when you say, for example, you're storing the result of rec sum 4, yes, it will set 10 as the result for there. And then you'll continue executing main. Perfectly. Yeah. So just a couple of quick things before I stop. I do apologize about this. Actually, let's stop here. And, oh, it's a 14. Let's see. 1 plus 2 plus 3. So we got 3, 6. Yeah, 10. I think we're... Either way, I'll let you check the example in the notes. Anyways, I do apologize. I'm just trying to get a little bit through this. I had it all going well, then we kind of just messed a couple things up at the last minute. It has to happen every single time. Perfect. Thank you. It's 10. That's what I thought. So, sorry, I got messed up on my green friend here. My lovely, lovely friend here. So anyways, when we come back, I'll talk about pros and cons of recursion, then we'll do an analysis of a recursive algorithm, okay? So I apologize for taking more of your time here today. When we come back, we'll talk more about recursion, okay? So I'll say thank you very much, and have yourself a beautiful day. I'll see you later.